By now you know C's syntax: cold variables, pointers, functions, structs. Level 3 is where that knowledge turns into real computer science, the data structures and algorithms every other language hands you pre-built, but here you'll see exactly what's happening in memory. We'll build a linked list, a stack, and a queue by hand, walk a binary search tree and a graph, sort and search an array the way the standard library does, and then go underneath all of it to see exactly how C's memory works and how it breaks. First stop, 3 structures you'll rebuild in nearly every language eventually. In Python or Java they're built in here. You allocate every node yourself, which means you also own every bug that comes with it. A linked list scatters its elements across the heap. Each node holds a value and a pointer to the next one. Push_front allocates a fresh node, points it at the old head, and hands the new head back to you. Forget to reassign it, and that node is leaked the instant it's created. Compiling with AddressSanitizer and undefined behavior checksum from day one is worth the habit. It catches the 2 bugs that account for almost every linked list crash, freeing a node before reading its next pointer, and using a pointer after it's already been freed. Forgetting to reassign head after push_front, freeing a node before reading its next pointer, and using a pointer right after you've freed it. 3 different mistakes, all traceable to the same root cause, memory that's yours to manage entirely by hand. A stack is simpler: 1 array, 1 top index, last value in is the first one out. Notice stack_push and stack_pop both return a status instead of throwing. C has no exceptions, so a caller that ignores that return value fails silently instead of crashing loudly. Push 1, 2, 3, and they come back out 3, 2, 1. The exact shape behind function call stacks, undo history, and the depth first search we'll use in a few minutes. A queue needs first in first out order, and popping from the front of a plain array would mean shifting every remaining element down by 1 each time. A circular buffer avoids that entirely, wrapping the index with modulo instead of moving any memory around. Even after the buffer wraps past the end of the underlying array, values still come out in the exact order they went in. It's the same trick behind ring buffers in audio and networking code. So which do you reach for? A linked list never needs a resize. An array-backed stack or queue gives you direct constant-time indexing and much better cache locality, in exchange for a fixed capacity. With lists, stacks, and queues built, it's time to build something with actual branching structure trees and graphs. Next up, structures with branching shape instead of a straight-line binary search trees for anything that stays ordered, and graphs for connections that don't form a hierarchy at all. A binary search tree keeps every smaller value to the left of a node and every larger value to the right. That ordering is exactly what makes search fast. Each comparison eliminates half of what's left, the same way binary search has a sorted array. Insert these 7 values and an in-order walk left node, right hands them back already sorted, which isn't a coincidence, it falls straight out of the tree's ordering rule. Find 40 and it's there, find 99 and it correctly comes back not found. Feed this same tree already sorted data instead, and every new node becomes the right child of the last one. You get a straight chain, and search degrades from log n all the way to n. Real self-balancing trees exist specifically to prevent that. A graph drops the strict hierarchy entirely. Any vertex can connect to any number of others, cycles included. This one uses an adjacency list, 1 linked list of neighbors per vertex, which is far cheaper than a full grid once the graph gets sparse. Breadth first search explores level by level using a plain queue, the same structure from the last section. Swap that queue for a stack or just recurse, and you get depth first search instead. Identical bookkeeping, a different order of exploration. Trees and graphs give your data real shape. The next question is speed. How fast can you actually sort and search what's sitting inside them? 2 algorithms nearly every C programmer implements by hand at least once: quicksort and binary search, plus the subtle edge cases that turn either one from fast to slow. Quicksort picks a pivot, partitions the array so everything smaller lands to its left and everything larger to its right, then recurses on each half. Average case that's n log n competitive with any general-purpose sort. 9 numbers in arbitrary order come back sorted in place, with no second array required. That's the whole appeal of an in-place partitioning sort like this one. This particular pivot choice, always the last element, has a specific weak spot. Feed it data that's already sorted, and every partition split becomes n-1 and 0, turning n log n into n squared. Production code picks a random or median pivot instead. Binary search only works on sorted data, but in exchange it finds anything in log n comparisons. Watch the midpoint math: low plus half the remaining range, not low plus high divided by 2, specifically to avoid signed integer overflow on large arrays. Search for 7 and it's found at index 6 immediately. Search for 42, which isn't in the array, and it correctly comes back -1 instead of looping forever. Quicksort's worst case is quadratic, but its average case matches merge sort at n log n without needing extra memory. Binary search needs sorted data first, but once you have it, log n beats a linear scan on anything but a tiny array. You've built the structures and the algorithms that move through them. What's left is the layer underneath. Every single one of them sees memory model itself. Every structure we just built lives somewhere specific in memory. This module makes that explicit, and shows exactly how the classic C memory bugs happen and the tools that catch them before your users do. A running C program has 4 memory regions. Data and BSS hold your globals, the stack holds local variables and shrinks the instant a function returns, and the heap holds anything you malloc, surviving until you explicitly free it yourself. Growing a heap buffer safely means assigning realloc's result to a temporary variable first, not overwriting your original pointer directly. If realoc fails and returns null, that mistake would both lose your data and leak the still valid original block. Read memory right after freeing it, and the program often looks completely fine. It just happens to still hold the old value, until the moment it doesn't. That gap between the bug and the symptom is exactly what makes use after free so miserable to track down. Compiled with AddressSanitizer instead, the identical bug is caught immediately: the allocation site, the free site, and the bad read all pinned down in one report, instead of a mystery crash minutes later somewhere completely unrelated. A leak doesn't crash anything, it's just memory that's allocated and never freed, so a long-running program's footprint keeps growing. Tools like Valgrind on Linux or leaks on macOS report every block still allocated when the program exits. One habit prevents most of these bugs: set a pointer to null immediately after freeing it. A null dereference crashes loudly at the exact line of the bug, and freeing an already null pointer is explicitly defined by the C standard to do nothing at all. From nodes scattered on the heap, to the algorithms that walk through them, to the memory rules underneath everything, that's the core of Level 3. That's 4 modules of Level 3 C: data structures, trees and graphs, sorting and searching, and memory management, each with runnable code and AddressSanitizer output you can reproduce yourself. Full write-ups and exercises for all of Level 3 are linked below, in the order we covered them today.